Welcome to the deep dive.
Great to be here.
Today, we're diving deep into something foundational for the modern web application architecture.
Yeah, how these things are actually built behind the scenes.
Exactly. Our source today is a set of lecture notes, web application architecture, and overview. Seems like it's from a programming course.
Applications and frameworks. Sounds about right.
And our mission really is to unpack these notes. We want to get a handle on core ideas like the three-tier architecture you hear about.
Absolutely. And look at the different layers the tech involved.
And grasp why certain choices are made, right? The goal is for you, the listener, to quickly get a solid feel for how the web apps you use every single day are put together.
Yeah, to see the structure underneath.
So let's kick off where the notes do. They make this fundamental distinction right at the start. What's the difference between a website and a web application?
That's a really important starting point. The notes say a typical website often just gives you static content. You read it, you look at it, like a blog or maybe a company info site.
Right, consumption.
Exactly.
Yep.
But a web application that's built for interaction.
Like online banking, social media, project tools.
Precisely. You're not just looking, you're doing stuff. You're interacting. And it's these interactive apps we're focusing on.
Because that interaction, well, it adds a lot more complexity, doesn't it?
It really does.
Yeah.
And to manage that, the notes highlight what's probably the most common structure today, the three-tier architecture.
Okay.
They call it the most popular form of N-tier or multi-tier architecture, basically breaking the application down.
Into three parts?
Yep. Three main tiers or layers, the presentation tier, the application tier, and the database tier.
Okay, let's break that down. Why three? What's the advantage of splitting things up like this for web apps?
Well, the notes give several key reasons. First off, each tier can run on its own infrastructure, physically separate.
Ah, okay. Not all lumped together.
Right. And because they're separate, well, different teams can work on each tier independently, maybe even at the same time.
So parallel development. That must speed things up.
Significantly. And it goes beyond just building it. Think about updates or scaling.
Right. If one part needs more power, like the database gets hammered.
You scale just the database tier. If the application logic needs more juice, you scale that. You don't have to scale everything just because one part is busy. It's much more efficient.
Makes sense. Resource management.
Plus, there's a security benefit. Compared to older, maybe two-tier models, this isolates your data and your core logic away from the part the user directly touches the presentation layer. Better separation, better security boundary.
Got it. Separation for manageability, scalability, and security. Okay, let's dive into layer one then. The presentation layer. You said that's what the user sees and interacts with, the front end.
Exactly. It's the client side, what's running in your browser, the user interface.
And what technologies power this, according to the notes?
Well, the foundation is the standard web stuff.
Yep.
HTML for the structure, CSS for making it look good, and JavaScript for making it interactive and dynamic.
The classic trio.
But building complex interfaces just with those can get messy fast. So the notes point out that developers heavily rely on frameworks.
Like React, Angular, Vue.js, those big names.
Precisely. Those are the popular ones mentioned. They provide structure, reusable components, ways to manage application state, basically tools to build sophisticated UIs more easily.
And they also mentioned some older tech.
Yeah, a nod to jQuery and AJAX, foundational stuff in their day, and you'll still find them in older systems, but less common for new builds compared to the big frameworks.
Okay, so that's the what. What about the how? How do you organize the code within this presentation layer, especially for big apps?
Good question. The notes talk about architectural patterns for the front end. Basically, establish blueprints for structuring that code.
Like MVC, I've heard that one.
Yep, Model View Controller is a classic. Also MDVM, Model View Model, and MVP, Model View Presenter.
They all sound kind of similar.
They share a core idea, separating concerns. Keep your data logic model separate from the display view and the user input handling, Controller View Model Presenter. It helps keep things organized.
Makes sense. Any other patterns mentioned?
Yeah, they also list component architecture, which is huge, with frameworks like React and Vue building UIs out of small, reusable pieces, and even micro front-ends.
Micro front-ends, like microservices, but for the UI.
Kind of, yeah. Breaking down a really large front-end into smaller, independently deployable units, it's a newer, more advanced approach for very large applications.
Interesting. Okay, so that's the face of the application. Let's move deeper. The application layer. If presentation is the face, is this the brain?
That's a great analogy. Yeah, this is the server side, the back end. This is where the core business logic lives, where the heavy lifting, the processing actually happens.
And what kind of technologies run here? Must be a wide range.
Oh, absolutely. Very diverse. The notes list some big players. Java, often with the Spring or Spring Boot frameworks. Node.js, which is JavaScript on the server, with frameworks like Express.js or Koa,
Python, .gpnet.
all mentioned. Python with Django or Flask. PHP with Laravel or Symfony. And the .NET framework from Microsoft. The choice really depends on the project, the team's expertise, performance needs, all sorts of factors.
And where does this backend code actually live? Where does it run?
Infrastructure options vary too. Could be traditional virtual machines, VMs, basically simulated computers. Or it could be more modern approaches like serverless computing.
Serverless, so no servers.
Well, there are still servers, but you don't manage them directly. You write your functions, your logic, and the cloud provider handles the provisioning, scaling, all that infrastructure stuff automatically. It's a different model.
Okay, got it. So presentation layer in the browser, application layer on a server somewhere processing things. But where does the data live? The actual information.
The third piece of the puzzle, the database tier or database layer.
This is the memory, right?
Exactly. The application's long-term memory. This is where you store persistent data. User accounts, product details, order history, posts, whatever the application needs you to remember.
So the application layer talks to this layer.
Constantly. It needs to save data here, update it, delete it, and most importantly, retrieve it to process requests or send it back to the presentation layer to show the user.
And what kind of databases are we talking about?
The notes don't list specific ones here, but generally you'd see SQL databases like PostgreSQL, MySQL for structured data, or maybe NoSQL databases like MongoDB, Cassandra for less structured data or different scaling needs. The point is, this layer is dedicated to managing the data.
Okay, that clarifies the three tiers: presentation, application, database.
Yeah.
But you mentioned earlier they need to communicate, especially presentation and application. How does that happen?
Right, the crucial connection. That's where APIs come in, application programming interfaces.
APIs. Hear that term all the time. What exactly is an API in this context?
The notes define it pretty simply. It's a software interface that lets different applications or different parts of an application talk to each other.
Like a translator.
Sort of, or maybe more like a menu at a restaurant. The presentation layer, the customer, looks at the API, the menu, to see what the application layer, the kitchen, can do. It makes a request, places an order, via the API, and the application layer sends back a response, the food, via the API.
I like that. You don't need to know how the kitchen works.
Exactly. You just need to know how to use the menu, the API. It abstracts away the internal complexity and provides a clear contract for how to interact.
And why are they so important? What benefits do they bring according to the source?
Huge benefits. Productivity is a big one for developers. They don't have to build everything from scratch. They can use existing services through their APIs.
Like using a payment gateways API or a mapping service.
Precisely. Need payments, use Stripe's API. Need Maps, Google Maps API. Need Weather API. It saves massive amounts of time and effort, which means lower development costs.
Makes sense. Reuse over reinvention.
And beyond just individual apps, APIs enable collaboration and connectivity across the whole digital ecosystem. They let different services connect and build on each other. It's fundamental to how the interconnected web works.
Okay. And are all APIs the same? Or are there different styles?
Different styles, definitely. The notes list a few common ones. REST APIs are probably the most widespread today for web services. They typically use standard web protocols like HTTP, very common.
What else?
WebSockets get a mention. Those are good for real-time, two-way communication. Think like chat applications, live sports scores, stock tickers, where information needs to flow back and forth instantly.
Okay.
Then there are older ones like SAPPIs, often more complex, XML-based, RPC, remote procedure calls, which is basically about running a function on a remote system, and a newer one, GraphQL APIs, which is interesting because it lets the client specifically ask for only the data it needs, which can be more efficient.
Wow, lots of options, but they all serve that purpose of connecting things.
Exactly. Enabling communication between components or systems.
All right, so we've got the layers, we've got how they talk. Let's zoom back into that application layer, the back end. You mentioned different ways to structure the code within that tier.
Right. Architectural approaches for the back end itself. The notes bring up three main ones: monolithic architecture, microservices architecture, and also service-oriented architecture, or SOA.
And you said the notes focus heavily on monolithic versus microservices? That's a huge debate.
It really is. The monolith approach is kind of the traditional way. You build the entire back-end application as one single large unit. All the code users, products, orders, everything is deployed together as one piece.
One build code base.
One big deployable unit. Think of it like one giant building housing all departments.
Okay, sounds simple initially, maybe, but the notes detail drawbacks.
Oh yeah. As that monolith grows, it can become really hard to manage. Development can slow down because the code gets complex internally, what the notes call local complexity. Hard to understand, easy to break things accidentally.
And scaling.
You can't scale pieces independently. If just the order processing part is busy, you have to scale the entire application, deploy more copies of the whole thing. It's inefficient.
What about reliability?
That's a big one. An error or a crash in one small module can potentially bring down the entire application. High risk.
Ouch.
Plus, adopting new tech is hard. Want to try a new language or framework? You basically have to rewrite or refactor a huge chunk of the monolith. It's expensive and slow, and even tiny changes often require rebuilding and redeploying the whole thing.
Okay, that sounds increasingly painful as things get bigger, so microservices is the reaction to that.
Pretty much. It takes the opposite approach.
Yeah.
The notes use an IBM definition, an approach in which a single application is composed of many loosely coupled and independently deployable smaller services.
So instead of one big building, it's like a campus of smaller, specialized buildings.
Exactly. A service for user management, another for products, another for orders, each its own small application. And the benefits listed flow directly from that. Well, services are small, independent, loosely coupled. A small team can own one or two. They can develop faster within their service.
And deployment.
Services can be deployed independently. Update the product service without touching the user service. Big win for agility.
Scaling must be better, too.
Yep. Scale each service based on its specific needs. Much more efficient use of resources. Reliability can be higher too. One service failing doesn't necessarily cascade to the whole system, though managing failures gets more complex.
And technology choices.
Big advantage. Polyglot programming. You use Java for one service, Python for another, Node.js for a third. Whatever makes sense for that specific job. You're not locked into one tech stack for everything.
Okay, microservices sound like the perfect solution then. Solves all the monolith problem.
Oh. If only it were that simple. The notes are very clear. No, it's not all sunshine and roses. Microservices bring their own set of very significant challenges.
Okay, like what? What's the catch?
The biggest one highlighted is high global complexity.
Global complexity, as opposed to the local complexity of the monolith.
Exactly. While each individual service might be simple inside, local complexity, managing all the interactions, the network communication, the dependencies between maybe dozens or hundreds of services, that's incredibly complex. Distributed systems are hard. That's the global complexity.
So you trade one type of complexity for another?
Pretty much. You're managing complexity between services instead of within one big service. And it's a constant operational challenge, monitoring, debugging across services, ensuring data consistency.
What other downsides?
Potentially higher infrastructure costs. You have more things running, more network traffic. Debugging is definitely harder.
Yeah.
Tracing a request that hops between 5 different services can be tricky. And the notes just kind of summarize it as a lot more, ... implying just generally more moving parts to worry about.
So it's a serious trade-off. No silver bullet.
Definitely not. The notes also give a quick mention to service-oriented architecture, SOA, which is kind of related, maybe a precursor, with slightly different philosophies. And they warn against an anti-pattern, the big ball of mud.
Big ball of mud. Doesn't sound good.
No. It's basically what happens when you don't have intentional architecture. A system that's just grown organically, become messy, tangled, no clear structure, something to actively avoid.
Right. Avoid the mud. Got it. Okay, besides these core architectural styles and layers, did the notes mention other supporting technologies, things that help make these web apps work well?
Yeah, they listed quite a few helpful pieces of the puzzle. Things like API gateways.
API gateways, what do they do?
They act as a single front door for requests coming into your backend, especially if you have microservices. Instead of clients talking to dozens of services directly, they talk to the gateway.
And the gateway handles?
Common stuff. Authentication, making sure the user is allowed in, rate limiting or throttling, preventing abuse, maybe routing requests to the right service, sometimes even combining results from multiple services, orchestration, caching common responses, gathering stats. It simplifies the client side and centralizes cross-cutting concerns.
Okay, useful. What else?
CDNs, content delivery networks. These are essential for performance. They cache static files like images, videos, CSS, JavaScript on servers geographically closer to your users, so that stuff loads way faster.
Right, makes websites feel snappy.
Caching tools are also mentioned, specifically Redis. The application layer often uses these in-memory caches to store frequently accessed data, so it doesn't have to hit the database every single time. Speeds things up, reduces database load.
Load balancers.
Yep. If you have multiple copies of your application server running for scale or reliability, the load balancer sits in front and distributes incoming traffic evenly across them. Prevents any one server from getting overloaded.
Message queues. Sounds like asynchronous stuff.
Exactly. They allow different parts of the system or different microservices to communicate without needing an immediate response. One service puts a message on a queue, another service picks it up later when it's ready. Good for decoupling tasks and handling background jobs reliably.
And underpinning all of this, the cloud.
Absolutely. Cloud computing is mentioned as providing the flexible infrastructure. Things like cloud storage for files, those virtual machines, VMs we talked about, serverless platforms. And the notes just say many more resources, which is true. Cloud providers offer a massive suite of services to build and run web apps.
Okay, wow, that's a lot of pieces. So let's try to bring it back together. We've got these layers: presentation, application, database. They talk via APIs. The application layer itself can be built monolithically or as microservices with trade-offs. And then there's this whole ecosystem of supporting tech gateways, CDNs, caches, load balancers, queues, all running on cloud infrastructure.
Exactly. And understanding how all these pieces fit together, the layers, the architectural styles, the communication mechanisms, the supporting tools, that really gives you a powerful framework for understanding how modern software actually works on the web.
Yeah, whether you're just using an app or maybe you're involved in building them or managing them, knowing this structure helps make sense of it all.
It demystifies things. You see past the slick UI and get a glimpse of the often complex but hopefully well-structured machinery running underneath.
It really illuminates the engineering that goes into those seamless experiences we kind of take for granted.
It absolutely does.
Okay, so quick recap of our deep dive then. We started with that key difference: interactive web apps versus static websites. We unpacked the very common three-tier architecture presentation application database and why that separation is so beneficial.
Right, the manageability, scalability, security aspects.
We looked at the technologies and patterns within the presentation, front-end, and application back-end layers. We stressed how vital APIs are for communication. And we spent a good chunk on the back-end architecture debate, monolithic versus microservices, and the significant trade-offs involved there.
Plus all those supporting technologies that make it robust and performant.
These really are the fundamental concepts behind so much of the digital world you interact with.
They truly are.
So here's a final thought, drawing from all this architectural discussion. Considering those trade-offs, especially the local complexity of monoliths versus the global complexity of microservices, how do you think this fundamental tension, this balance between having independent, manageable parts versus the inherent difficulty of coordinating them, how does that shape the future of web development?
That's a great question to ponder.
What does that ongoing push and pull mean for how we build apps that aren't just cool, but also resilient, maintainable, and genuinely scalable as the world keeps demanding more? Something to think about next time you're clicking around online.